Hello, this is Group 5 and we will be presenting the ECE Building Construction Plan. The group is myself, Omar, Kinda, Fadi, and Mohammed. We will first start with the introduction. The ECE Building, or the Electrical and Computer Engineering Building, first started construction in 2011. It was officially concluded in October 10th, 2014, and had an estimated total of $95 million, with around half of that financed by the state of Illinois. It consists of 5 floors, 1 basement, and around 230,000 square feet of usable area. This includes 20 labs, a grand lobby, conference rooms, and multiple open workspaces. It is built using mainly granite, bricks, glass, and steel. This material is recycled and all regionally sourced. The first section of this plan is the mobilization part. Okay, for the site context, the ECE building is located at the western corner of the North Quad. It overlooks Wright Street and its address is 306 North Wright Street in Urbana. It's surrounded by Beckman Institute to the north, the Coordinated Science Lab to the east, and the Micro and Nanotechnology Lab to the south. It's serviced by 2 main roads, the Wright Street and to the west, and the Eastern University Avenue to the north. On to the site limits. As seen in the Google Earth screenshot, we can annotate the site limits on this picture. First, you can see the yellow line. It shows the total site area. This was determined using Google Earth time-lapse and delimiting the fence markings that were able to be seen. Next, you have the dark red polygon. It represents the main building area of the ECE building. Then you have the pale red polygon. It represents the secondary building area. Then you have the 2 small red polygons on the left of the image. That's on Wright Street. These are the main entry and exit gates used by the trucks. More details regarding the path is explained later. The small black polygon shows the material below the material gates is the pedestrian worker entry to the site. Then you can see the blue polygon is the likely position of the temporary office spaces. And then the 2 yellow polygons are the staging areas. The larger one on the quad is material staging, while the one closer to Beckman is the equipment staging area. Note that the second equipment staging area is a potential location just from images of the construction site and the coming sites. Here you can see the basis of the previous claims. You can see that the image on the right shows the temporary office, the white structure, with the Beckman in the opposite direction, meaning those offices are to the south of the electrical building. And then the other 2 images showcase the material staging area being alongside the quad and the east of the building, as well as the equipment staging near Beckman Institute. In this image, you can see an excavator in the back in front of the building being built. This suggests that the area could have been used as an extension to the equipment stages, especially as we can see material being hauled around near Beckman too. The type of fence chosen is a chain link fence. Chain link fences provide transparency and also helps develop interest into the project by people passing by. The chain link fence is easy to place around the site and has sliding gates for vehicular access. It also has swing gates for pedestrian access. This image, as you can see, also shows the northernmost vehicular gate that was showed in the previous image. Here you can see the signing on the fence below. This signing acts as a source of information on the building's function. It showcases the future appearance of the building, and it also serves as a warning instructions, which will also be shown on the next slide. As mentioned before, fences hold warning signs. So the left fence has a red sign that says restricted area, keep put, and the right sign, as seen, has sidewalk closed. Next, onto the material hauling route. There are 2 possible material hauling routes. The first one you can see in front of you, hauling route 1. It's a 9-minute average drive along Springfield Avenue until you reach the Campus Instructional Facility, or the CIF building, where you turn left on Wright Street until you reach the ECEB's main vehicular entrance. However, this route has an issue, which is denoted by the black circle on the image. There is a railway crossing there with a maximum 11 foot 10 inches height clearance, which is too low to allow a safe passage of hauling trucks. So we're actually going to go to Route 2 on the next slide. Here you can see hauling Route 2. It's a slightly longer route with 10 minutes average travel time and requires more turns, making it more complex. However, it has no issues on the way. It goes through University Avenue until Prospect Avenue, and then you reach Wright Street and turn right to the ECE Building. It does increase the complexity of the route, but it's a safer route with no obstructions and throughout all major highways. Okay, based on the following image, first of all, a truck coming into the north gate and going into the pale red area, which has a lower altitude than the rest and is overall empty, may be able to deposit some material or equipment at the location and turn around and exit from the same gate onto Wright Street and back on Route 2 mentioned above, which are the orange arrows. The second thing is a truck entering into the south gate would deposit the material and or equipment at their designated areas and loop around the building before leaving from the north gate onto Wright Street and then follow along Route 2, which is the blue arrows. So after the mobilization plan, we have the site and excavation plan as follows. As you can see in the image in front of you, these are all the identified utilities on site, and there's a legend where the red is the underground electric lines, the yellow are the gas lines, the orange are telephone lines, and the blue are potable water, purple sanitary and irrigation line, and green is a storm sewer line. Then you can also see where there's a utility replacement for the Beckman connection, since it's a new building. And you have to note that before starting any excavation work, site utilities should be rerouted, protected to a place that will not be affected by construction activities. After we have identified all the present and needed underground and overhead utilities on the site, then we have to determine which ones are going to be disturbed and need to be rerouted. First, you have the sanitary sewer line, the water line, the gas line, the telephone line, the storm sewer line, the overhead electrical line, the underground electrical line, the communication line, and the SBC communication line. These utilities are owned by different companies, and all the contact information and addresses of each utility owner is provided in the table shown in the slide. Onto the equipment required for site cleaning. First, we have the crawler-based dozer, which is used for removing trees of large size and concrete waste from the sidewalks. Then we have the excavator, which will be used for clearing stumps. And then we have the disc-style wood chipper, which will help cut down trees. For the demolition plan, as you can see in the plan in front of you, you can see all the types of demolition that will occur and where it will occur according to the legend and the highlighted place. Based on the demolition plan in the slide before, some of the items that are going to be removed are as follows: trees and hedges, parking meter and foundation, which is coordinated by the city of Champaign, sanitary manholes, electric lines, concrete curbs and gutters, and light poles and foundation. However, some items are going to remain and be protected. Some of them are trees beyond the structure, the water main, and specific structures and associated piping. Next, for the excavation, we have to calculate the volume of excavation. This was calculated based on the average length, average width, and depth of excavation, while also assuming the sloping of the sides, which is 1:1, and providing 3 feet for working space. The soil type was assumed to be loam, with 25% swelling factor. So, as follows, the total volume, or the estimated excavated material to be removed, was about 63,856 loose cubic yards. So then, for selecting the equipment required for excavation, we start by determining the production of the excavator based on the heaped bucket volume, job, and management conditions, bucket fill factor, and number of cycles per hour. Then we determine the number of excavators needed based on the volume of excavation on site, Then, to determine the number of trucks and loaders needed, we computed the total cycle time of the truck. Then we determined the number of trucks required by dividing the total cycle time by the load time of the loader, which then ended up having 8 trucks and a loader so that the truck productivity is governing. So the total equipment required are 8 trucks, 1 backhoe loader, and 3 excavators. The truck volume was 16 loose cubic yards, the excavator volume was 2.5 cubic yard buckets, and the loader had 2.5 cubic yard buckets. Then onto the excavation phasing plan. This can be completed in 4 phases. First phase is site work, then the part A of the building, then part B of the building, then demobilization. Phase 1, which is the site work, first of all, you contact the call center known as Julie to request a remote ticket entry at least 48 hours before needing to dig. Then you coordinate with Julie for a temporary shutdown. They will also handle the schedules with the utility locator service, which takes 2 working days. All of the public utilities will be marked by a utility locator. Then you reroute and relocate all necessary services. Then on to phase 2 of the excavation phasing plan. You have the building section A, which is the north part of the building. The excavation work will start by surveying the area, setting corner benchmarks, coordinating the trucks, creating a ramp for trucks to move in and out of the site, which specifications of the ramp are on the slide. And then you have a storing earthwork area for backfilling. Then on to phase 3, which is section B of the building, which is the south part. As soon as section A has finished, the excavating will begin for building section B, and it will follow the same steps that were outlined in the slide before. Now, lastly, for the demobilization, before excavation has finished by a couple of weeks, you have to coordinate with the lowboy or necessary trucks needed to haul the equipment off the site. Before you begin to remove the equipment, you have to make sure none of the equipment being used are going to be used for the next phase, so you do not relocate or remove it off the project when you still need it. For the project, you have to keep at least 1 excavator, backhoe, skid loader on site to help place the filling material and help move material on the site. After the site work and excavation, we then go on to the foundation part. Now for the foundations. The first step to any construction is the foundation. First, we have to analyze what the foundation needs. First, we map the groundwater underneath the surface, which will tell us where the best places are to begin drilling a sump pump to prevent water from collecting in the basement. We then select the design working life, which is usually around 100 years, which is category 4 according to the Eurocode, as structural examples, including monumental buildings and civil engineering structures. Since it's not a very tall building or a skyscraper, there are only vertical loads and very few shear loads. Also, a soil survey will be done to find out the soil bearing strength. And then you have to see the frost depth, which is also calculated by consulting historical data to determine the minimum depth for the foundation. Next, for the footing selection, according to the soil condition and the load calculated for the superstructure, the suitable foundation system required for a project is shallow foundations or shallow footings, since the soil is relatively firm under the structure. This 4-story structure must have at least 100 kilonewtons per meter squared bearing capacity to consider the shallow foundation. This project in particular will have a combination of isolated and combined footings. For the equipment required for the foundation stage, first you'll need a vibratory compactor, which are used to compact the soil to its proper density. Then for pouring the Sabon grade foundation, a concrete conveyor is used. Then you also need a vibratory rammer, which are used to reduce air spaces in concrete, which is then followed by the screeding. You also need a power trowel, which are used to float the screeded surface and then provide a finish to the slab. Lastly, you also need a total station to measure angles and distances from footing to retaining walls. Additional equipment required are concrete pumps, which are used for pouring concrete. This specific pump in the picture is chosen because of future calculations. You'll also need a dump truck for transporting, a backhoe loader for digging, loading, and transporting and excavating. And you also need a crawler excavator, which is used for trenching, loading, and lifting. We will also need a telescopic boom lift, which is used to reach high vertical places to access the retaining wall to place the reinforcement and the formwork. You also need the vibratory rammer, which is shown in the image and talked about in the slide before. And you also need a telehandler for material handling and movement. Now for the phasing plan of the foundation installation. First, the property is graded and the foundation is dug. Once the footings are set and pass inspection, a contractor will pour the concrete into the home's overall foundation. Then the polystyrene blocks are installed for pouring insulated stem walls. The ground inside forms are prepped for the slabs. Then the plumbing pipes are run under the ground and stubbed up in the exact locations. Plastic tubing is laid for the radiant heat, and the concrete is pumped into place, and the site is cleaned up and prepared for the framing crew. For the building foundation phasing plan, the foundation will start from west to east within each phase. So they are split into two phases as shown in the figure. And then for the first part of the foundation will start with the footing on the north side. After the footings, the retaining wall on the north side, and in parallel, the south side will also start with the footing and then onto the retaining wall. After completing the retaining wall on the north side, the slab on grade is placed and cured without disturbing work on the other side. Now for the concreting plan. The total concrete requirement is 4,500 cubic yards. We are using 10 cubic yard concrete mixer trucks, so we need 450 trucks for the foundation part. This will be done in an interval of 15 minutes to avoid congestion. They'll also have nighttime transportation of these trucks. The material will be stored in the south phase of the project to work in the north, and then vice versa when working in the south. The material will be unloaded with the help of a telehandler. Then for the reinforcement material, the steel is unloaded in the staging area, then placed. And then since everything is cast on site, there will not be any prefabricated concrete items. Lastly, for placing the formwork, a telescopic boom lift will help access the heights for placing this formwork. For the footings construction process, first you have to locate the footing using a total station. Then the materials are transported using a mobile crane. Then you have the steel cutting equipment which cuts up the reinforcement and is placed. Then the formwork is placed. Then the plates are cut using the steel cutting equipment at site, and then they're arranged. Then the concrete is poured using concrete pumps, and the vibrators are used to compact the concrete. Then as soon as the concrete hardens, prefabricated rebar is then placed in the position. Then the formwork is removed and the concrete is cured. Then the backfilling is done with a backhoe, and then a compactor is used to compact the soil. And then onto the retaining wall. The retaining wall is built with the same process. However, the ground is compacted using water, and then the compactor will ensure that there is like a firm base for the concrete. This also helps to reduce the water absorption by the soil. Then the reinforcement is done according to the drawings or the design drawings. Then after that, the curing is also done using a water pond. Lastly, for the demobilization of the equipment, you have to return or relocate the equipment and materials. You create a list of materials that the company keeps as a part of the property and what is being sold or reused. The debris and the waste materials are then disposed of from the site. Then you remove the machinery once the work is done to create a pathway for anything to pass. And then halfway through the construction of the right part of the retaining wall, the machinery and materials are moved to the ground level storage to start the structure of the columns. Again, you have to make sure that none of the equipment or materials are going to be used later in the project before disposing of them. Now that the foundation part is done, we move on to the superstructure part. For the ECEB superstructure, it consists of 5 floors in a U shape. The building can be divided into 2 parts. Part A, the top 2 rectangular parts, as shown in the figure, and then part B is the middle square and the bottom rectangular part. The building is 209 feet in length and 240 feet in width. The main components of the ECEB superstructure are the I-shaped steel columns and the steel outer structure, the main steel girders, the secondary steel beams, the composite steel decks, which are 3-inch metal sheets and 4.5 inch of concrete, and the roof metal decking, which are 1.5-inch metal sheets. As mentioned before, the ECE building has a vast amount of concrete. As you can see here, the concrete calculations for each floor. You have the first floor having 622 cubic feet of concrete, floor 2 having 558, floor 3 having 666, and floor 4 and 5 having 311.8. For the ECE building, it has a typical framing plan with the main girders in the blue on the outer skirts of the building, which are connected by secondary beams that are shown here in green. This is similar for both Part A and Part B. Then we have the equipment needed. We have the crawler crane, which is used for heavy steel erection, like the columns. Then you have the truck-mounted crane for miscellaneous superstructure lifting and easier, lighter structural lifting. Then you have the concrete pump for pouring concrete and composite decking. Then you have the concrete trucks for transporting concrete to the site. Then you have the telescopic lift, which is used for steel connection installation. For the crawler crane selection, we went with the Link Belt 138 Highlab HSL. This was chosen first according to calculating the column weights. As you can see, the heaviest column, CG3, was 4.93 US tons. So we had to make sure that the crane can carry more than 493 US tons. And then you also had to make sure that the boom was longer than 127 feet, which is the height of the building. So accordingly, after checking the technical details of the crane, we saw that it had a 200 feet boom and can carry well over 5 US tons. Next, for the truck-mounted crane selection, we have the Linkbelt RTC 8050 Series 2. This was chosen according to the boom length and the max weight needed for assembling the crawler crane. So after checking the boom length and the radius of rotation, we saw that it was able to carry well over and assemble the crawler crane. So next to the concrete pump selection, we chose the Pump Partners Model 65M. This was chosen according to the height and reach. Since the maximum pouring height is 110 feet, so we chose this because it has a reach of about 180 feet, which is more than the width of the site. And then it can pump concrete to the farthest point on the highest floor if placed within the building boundaries. Then, while coordinating with the site layout, knowing the pump's dimensions, as seen as in the upper right of the picture, we selected 3 pump locations for each of the quadrants shown in the photo. So, for example, the top location would be able to access both the top 2 quadrants with ease, and then the right location would have the 2 adjacent quadrants, and the one on the left would have the whole strip. Then for the final 2 equipments needed, you have the concrete truck, which is the Prairie Material Ready Mix truck, which we mentioned before was 10 cubic yards, and since it is easily locally sourced. And then we also chose the JLG 1350 SJP Ultra Series telescopic boom, because of its length and achievable height. Next, as we mentioned before, we are going to split the superstructure phasing plan into Part A and Part B. As you can see, the Part A is the north part and the Part B is the south part. Then onto phase A, the process will go from west to east. It will go inward from the main street. It will go from part 1 to part 2 to part 3. First, it will start with a part 1 steel erection, which is the steel columns and so forth, and then the decking and then the composite slabs, going from part 1 to part 2 to part 3. Then, for phase B, the process will go the opposite of phase A. It will go inwards, outwards. However, then it will go from 4 to 5 to 6 to 7, which is from east to west, then back to 7. It will start with a steel erection in phase 4, then the decking and composite slabs, and then ending with the decking and composite slabs of phase 7. Next, for the steel storage, you can see that the steel storage, as indicated by the drawing, is in the bottom right of this drawing, which is in the north quad, within the site limitations. It's put there, or the storage was there, because of its easy access, where the crane can access the steel and then place or erect the columns easily throughout the building. Now, after the superstructure, we'll be talking about the electrical part. First, for the electrical system components, the major components of a building's electrical system can be grouped into 3 categories: power handling equipment, wiring and raceways, and utilization equipment. Here we will discuss the power handling equipment. The first step in developing a building's electrical system is to examine how electricity is brought into a facility. The two main ways of feeding a building with electricity is from a utility line, either through running an overhead or an underground system. In this case, the ECE building, the system is used as an underground system through concrete ducts with separators or spaces. This can be seen in the slide in detail 3, duct bank detail. Then, there are two main feeding points, as indicated in the drawing, as input locations: the primary feeder and the emergency one. Also in this project, a new manhole is to be constructed as shown in the drawing, along with new ducts connecting the main feeding manhole and the power inlet, and also connecting the emergency power inlet and the generator. Now, after connecting the main feeders to the main electrical room and the emergency room, which is shown in the figure, the main components of these rooms can be analyzed. The most important component to deal with is the unit substation, which is an assembly comprising of a primary voltage switch and fuse, or circuit breaker, a step-down transformer, metering equipment, controls buswork, and secondary low-voltage switchgear. The main function of this assembly is to accept an incoming high-voltage power supply, transform it to a lower one that can be utilized in the facility, and then distribute the low-voltage power through associated low-voltage switchgear. It is important to consider the placement and assembly of the unit station as soon as the substructural work of the basement is done, as it might require the use of a crane. Another important component of power handling systems are switchboards. Switchboard is a large, freestanding assembly of switches and fuses. The different types and comparison of the circuit breakers and switch fuse are going to be discussed in detail in the report. Then, moving on to the electrical distribution panel, it is essentially the same as a switchboard, but on a much smaller scale. Then, after the electrical distribution panel, you have a smaller panel board for floors, and they keep on getting segmented for each area. Lastly, for power handling, there are the emergency and standby systems. These use either two systems, an engine generator set or battery equipment. For the ECE building, the use system is the engine generator, which is a diesel set system, where a generator is connected to a main switchboard in the emergency electrical room, which runs on diesel. Then, there's also an important note about the diesel generator. It has a concrete pad that has to be designed and poured on site prior to the room being built. Then, onto the next group of components are wiring and raceways. The wiring and raceways are responsible for carrying the current throughout the whole system or throughout the whole building. These connect all the groups mentioned before electrically. For the wiring, the most common conductors used in wiring are aluminum and copper, and then they are usually insulated by various materials, depending on its use. These insulated wires can either run freely and can be boarded or nailed to whatever area they're in, or they can run in raceways, which are basically cable trays holding certain wires. For the last piece of the electrical system puzzle, you have the utilization equipment. The utilization equipment is essentially what uses the electricity fed to the building. So some of the examples of these systems are fire alarms or fire alarm systems, lighting, which are usually either normal lighting fixtures or emergency fixtures. You have pumping, you have HVAC systems like the air handling units, thermostats, and other machinery. You have audio and visual sensors like either TVs or projectors or whatever. You have telecommunication devices, and then you have outlets and device boxes. All of these are just utilization equipment which finish the electrical system components. Next, we have the electrical system phasing plan. This is split up into 5 phases. The first phase, which is the equipment installation. At this phase, after the foundation and basement walls are done, major components such as unit substations, emergency generators, large switchboards, and distribution panels are put into place with the help of a truck-mounted crane. This also includes the stage where the ducts and conduits are also constructed. The second phase, which is the distribution elements, is where the distribution of the electrical elements are placed. In this phase, all elements such as switchboards and panel boards, wiring trays, disconnect switches and junctions are installed. Third phase is the pull wires and terminate panels. This is where before the sheetrock is placed, and at the stage, all wires are pulled to place and most panels are terminated. The fourth phase is the trim out, in which all accessories, fixtures, and utilization equipment are installed and connected to the building's electrical system. By the end of this stage, the entire electrical system of this building should be working efficiently. Last stage is the power and testing. Obviously, when you install any system, you have to test it to make sure that no fuse will break or bust, and nothing will go wrong. Now onto the electrical system equipment required. There are 3 main equipment required. First is the truck-mounted crane, which will already be there, servicing the site. It's used to move and put all heavy electrical components into place. Then you have the concrete pump, which is used for pouring underground concrete ducts and for pads for heavy machinery. Then lastly, you have scissor lift, which helps access high places where you would place equipment or machinery. You may also need some minor or other special equipment. These are used throughout any other secondary construction, like electrical, mechanical, and plumbing and fire protection. These equipment are like common tools and equipment like drills, wrenches, and so on. You also need lugs, coax connectors, splicing connectors, and terminal blocks. You might need fishing rods or cable pullers, electric conduit benders, and then voltage testers and other machinery that are used for testing and circuit finding. Then lastly, after the electrical, you have the plumbing and fire protection. For the plumbing and fire protection system, the system components can be split into 3 types. You first have the piping. You have sanitary piping, drainage piping, which is for rainfall and other wastewaters. Domestic water, which is split into hot and cold water piping. You have nitrogen piping and compressed air piping. Then you have, for the equipment, you have a sump pump, a water pump, nitrogen storage tank, air compressor, vacuum pump, and neutralization tank. Then, for the fixtures, you have drains, either floor or roof drains. You have bathroom fixtures like urinals, lavatories, and sinks, and any other adjacent fixtures. And then lastly, you have valves, which are placed in pipes. Now, for the equipment used in the components of the plumbing and fire protection system, first you have the sump pump, which removes the wastewater from below ground level. Since drainage and sewage systems are usually based on gravity, anything below ground level needs a pump to pump it back up. Then you have the vacuum pump, which removes air from space, either for fire protection to change the pressure, so to avoid the fire going there, or to eliminate corrosive gases or any other materials. You then have an air compressor, which compresses air to increase the pressure. It's either for fire protection or for eliminating any other odors or corrosive gases. Then you have a neutralization tank, which changes the pH level of corrosive water. Since this is an electrical and computer engineering building, they might need neutralization tanks in certain labs. Then, lastly, you have a water pump, which pumps the water or the domestic water, either hot or cold, throughout the whole building. Then, for the equipment needed, which is fairly similar to the electrical equipment needed, you need a mobile crane to haul material. You'll need an electric scissor lift to access high places to install equipment. Then you either need a forklift or a pallet jack, depending on the size of the equipment needed and depending on the mobility of where you're going to install this equipment. And then you will need other miscellaneous equipment, which was mentioned in the electrical part, but one key miscellaneous equipment is a drill. Okay, for the plumbing phasing plan, the plumbing will be installed bottom up, like the building. The first phase will be installing the equipment and connecting it to the main water source or the public water source, which is offered by the city of Champaign or the university. This is both for the drainage and the domestic water system. And if there's any demolition or tie-ins to adjacent buildings, we will start off first with that. Then for phase 2, the piping will be installed also bottom up, so you go from the basement to the first floor and then all the way to the roof, ending with the roof drain and the piping on the roof. Then lastly, you'll have the plumbing fixtures installed. This ranges all the way from the lavatories and the urinals, the sink, to the drains, to any fixtures that remain. All of this must be done before the gypsum board is placed. After placing all these systems, there will be a pressure test and a flow test for all the plumbing equipment to make sure that the building is running smoothly and the plumbing is running smoothly. Then onto the fire protection plan or phasing plan. The first phase will include the demolition and connection to the fire protection system tie in the Beckman Institute as seen in the figure below. This is done during the foundation stage. Then for the second phase starts after the plumbing, piping, and HVAC is installed. This includes the installation and connection of all the pipes and sprinklers for the wet system, and also connecting the piping and dissipation system for the dry system to the main HVAC system. Then lastly, for the fire protection plan, you have the testing phase. The testing phase is a very crucial phase for the fire protection phasing plan because it's always better to be safe than sorry. Then you have to test the system very well in case of a future fire. This is done before completing the drywall in the building. And that is the end of our project. Thank you, and please contact us if you have any other questions. And lastly, here you can see our references.